Hi, I'm Daniel Chan from UNSW Sydney. Welcome to another adventure in pure mathematics. In this video, I'm very pleased to talk about the Galois correspondence, which is one of the key results in Galois theory. It is a result which allows you to use symmetry to tell you a lot about field extensions. Okay, so let's look at our setup. So what we'll consider here is K over F is some sort of finite field extension, and we can look at G, which is the Galois group of K over F. That is the group of all automorphisms of K which fix every element of this subfield F. And what we want to do is we want to set up a correspondence between two different sets. So what are the two different sets? So on the one hand, we want to study this field extension, K over F. So here we have K, and here we have F. And what we're going to look at is what's called the set of intermediate fields. So they're going to be the set of fields L sandwiched in between these two. In other words, L is going to be a subfield of K, which also contains F. That's an intermediate field. Okay, so let's suppose in this correspondence we're given L is an intermediate field. Okay, so it's a subfield of K containing F. What we're going to do now is we're going to define a subgroup. Okay, that's part of the correspondence, and also it's a correspondence, so we can also come back. So given a subgroup, I also want to define an intermediate field. Okay, so let's see what happens going in this direction. Okay, going in this direction, what I do is I take this intermediate field L, and I'm called L prime the corresponding subgroup of G. And what is that? That's just the Galois group of K over L. Okay, the Galois group of K over L. Okay, so let's just try to process this, or what's involved here. So the Galois group of K over L, what is that? It's the set of field automorphisms of K. So remember, G is field automorphisms of K fixing F, but these are the field automorphisms of K fixing all of L, and in particular F. So in particular, these Galois automorphisms of this, okay, are also Galois automorphisms of K over F. Okay, they certainly fix F because, in fact, they fix all of L, those field automorphisms. And of course, we know this is a group under composition, so it is actually a subgroup of G. Okay, so in that way, we get from an intermediate field, we can get a subgroup of G. Okay, and now we want to go backwards. Okay, that's the reverse part of the correspondence. Okay, so given H, a subgroup of G, we're going to get an intermediate field. And how do we do that? And that's via a procedure that we've seen also before. Okay, and I'll denote this coming back also by a prime. This is useful notation that you'll see in Kaplansky's treatment of Galois theory. And how is this defined? Okay, what you're going to do is we want a subfield of K, and one way we can do that is we can just look at the fixed field. Okay, H is a group of automorphisms of K because H is a subgroup of G, so you can look at that fixed field. So certainly that'll be a subfield. Okay, so that's how we come back from H to H prime, which is KH. And I guess what you have to do is you have to check that this is actually an intermediate field, so it contains F. Okay, so it contains F here. And why does it contain F? Okay, so remember, the only thing that you look at things fixed by elements inside this H, okay? But all of these elements here, because H is a subgroup of G, are Galois automorphisms, so they certainly fix all of F, okay? So certainly F is contained inside this, okay? So you do get an intermediate field in that way. Okay, so that's very nice. So there's a very strong relationship between intermediate fields of this field extension and subgroups as given by this correspondence. And what we want to do is we want to study it, and in particular see when this is actually a bijection. Okay, so let's just do a little example so that you can see what happens. So in this example here, I'm going to look at a splitting field of x cubed minus 2 over q. So basically I'm going to join to q, cube root of 2, cube root of 2 times zeta, which is the primitive cube root of unity e to the 2 pi r 3, and cube root of 2 zeta inverse, the conjugate of this root here. Okay, so that's also q adjoint cube root of 2, and this zeta, this primitive cube root of unity. Okay, so that's the field extension is going to be k over q. We can look at the Galois group of that, and we've seen that this is a Galois extension. Okay, so it's separable because you're in characteristic 0. It's also a splitting field, so it's normal, so it's a Galois extension. And in this case, the Galois group is isomorphic to S3. It's determined by what it does to these two generators, or these three generators, if you like. And the point is that you can permute these any way you like. Okay, so and that will completely determine it. Okay, so it's basically S3, or more precisely, perhaps the way you should think of it is permutations of these three roots of x cubed minus 2. Okay, so let's just pick a subgroup inside here. We're going to pick a subgroup that corresponds to the cyclic group generated by this tau, which swaps these two roots, cube root of 2 zeta and cube root of 2 zeta inverse. Of course, if you think about what this does, all this does is that it swaps this to its complex conjugate. Okay, so actually, this is just conjugation restricted to this field. Okay, so you can certainly see that conjugation will restrict to this field. So what is this tau prime? Okay, so this group generated by tau, if you look at prime. Okay, so what does the priming operation do here to a group, subgroup? Okay, you look at the fixed field. So you look at things fixed by tau. So of course this is just k fixed by tau equals k intersect r. And that's just the intermediate field. Okay, so what intermediate field is that? Well, of course, you're just looking at all the real elements inside here. Cube root of 2 is real, and if you think about it, that's the only thing else that you can get. Okay, and that's quite easy to see if you use this description of what this is. Okay, this allows you to have a basis consisting of the powers of cube root of 2. That's the 0th power 1, the first power cube root of 2, and the second power. And you can also multiply those three powers by either 1 or zeta. Okay, and of course, when you look at that way, you can see that what are the real elements are just those things which are generated inside here. Okay, so that's one example where we start with the subgroup of the Galois group, and we get an intermediate field, and the intermediate field is quite easy to write down like that. Okay, so let's have a look at something else here now. We're going to look at an intermediate field. It's going to be not Q adjoined this cube root of 2, but let's just say we pick this cube root of 2 zeta, and we look at the prime of that, so we want some subgroup. So what's that subgroup? So let me tell you what the answer is in that case. So of course, what happens when you prime here? What do you want to do is you want to look at the Galois group of this K, but not over the Q, but over this. So what are the Galois automorphisms, okay, which fix this cube root of 2 zeta? So you want a subgroup of this S3, the permutations of these three roots. So what permutations of these three roots is going to fix that? Of course, it's the only non-trivial one is the one which swaps the outer two roots. So you look at the thing which is generated by, let's call it tau 1, which swaps cube root of 2 with cube root of 2 zeta inverse. And that's the subgroup that you get, okay, generated by this order 2 element, this involution. Okay, so I hope you've got a little bit of feel for what this correspondence is, how this is set up and defined. Let's look at some basic facts about this correspondence. And of course, it's going to be most useful when this correspondence is actually a bijection. And we'll see that later. Okay, so given some basic facts, okay. Suppose you have, instead of just one intermediate field, you have two, and they're in a nested pair like this. Okay, L is contained inside L1. Then you can ask, what about their corresponding subgroups, L prime and L1 prime? Are they related? And the answer is yes, and actually they're related. There's also an inclusion relation, but it gets reversed. So here L was the smaller one, L prime now is the bigger one. So L contained in L1 implies L prime contains L1 prime. The other thing is, well, of course you want these to be inverses, so you can ask, well, when you prime to get from an intermediate field to a subgroup, and then prime again to go from that subgroup to an intermediate field, do you get back to itself? And in general, unfortunately, the answer is no. But what you do always get is this inclusion here. L is contained inside L double prime. Okay, so that's something that's rather nice, that at least it's not too far from being a one-to-one bijective correspondence, okay, because you have this, and this already says that it's going to be useful fairly generally. Okay, so that's starting from the side of the intermediate field. So let's start from the side of the subgroups. Suppose you have H is a subgroup of H1, which is a subgroup of of G. Okay, then you can look at the primes of this, H prime and H1 prime, and again, what you'll see is that there's this reversal of that inclusion, but you still at least have a relationship. Again, what you also find is that, well, you can compare H with H double prime, and again, you'll find that there is this containment. When you double prime something, it gets bigger. And in fact, in some technical way, it's actually a closure operation. Okay, so if you have this process of taking the double prime, if you do it again, actually you don't change. Okay, so let me make some important remarks about what's going on and also say something about the proof. The proofs of 1 and 2 actually, they just follow from definitions and they're fairly similar, so we'll just go through that. And so maybe we'll just have a look at this one here first. Okay, this part here. So what's L double prime? So the first L prime, if you go to L prime, is just a Galois group of KL. Okay, that's the subgroup you have, Galois group of KL. And then when you prime it again, so that's that subgroup, you've got to prime it again, you look at the fixed field with respect to that subgroup. So it's K fixed by Galois group of KL. Okay, so that's what you have. And of course, one of the things that we saw is that, of course, this fixes all of L, all right? All the automorphisms here certainly fix L. So the fixed subfield certainly contains L. So this L double prime that we have here contains L. Okay, that's one direction that you have there. And the remark that I want to make here is that what happens in the case of equality, actually, that's a situation we've seen before. Because what does equality mean? If you look at K over L, you think of that extension, and you ask, when is it Galois? It's Galois precisely when the Galois group of K over L is sufficiently big in the sense that you look at the fixed subfield of this Galois group, and it gives you back the original L. Okay, so the situation where L equals L double prime is just a situation that K over L is Galois. Okay, so that's a rather nice reinterpretation of what goes on, and that's part and parcel of the theory. Okay, so we've done this part of part 1. What about the other part here? Okay, so we want to say it reverses inclusions. Okay, so let's have a look and see what happens if you start with L here and you increase the size. So you start with L here, and what we're going to do, we're going to apply prime, but we're going to increase the size of L from L to L1. Okay, so what is this Galois group? It's this group of automorphisms of K which fix L. Okay, so the bigger that you make L, if you increase L to L1, it has to fix more things, so it can only get smaller, and that's why you have this inclusion. And I'll leave it as an exercise. It's similar following definitions that gives you part 2, and that gives you this basic fact. So the way you sum up this basic fact is that you have this correspondence. It's not a bijective correspondence in general, but what it certainly does is that, firstly, it's not just a bijective correspondence that looks at the sets, these two sets. These two sets also have a poset structure on them. Okay, they're ordered by inclusion, and what this correspondence does is it reverses inclusions. Okay. The other thing is that no, it's not always a bijection, but what happens is that when you double prime and you come back, you get something that is at least as big as the original. Okay, that's how you should think about this fact. Okay, so let's get to the very important Galois correspondence. That's the main result in Galois theory, okay, as it is set up. Okay, so we're going to start with K over F. Is some finite Galois extension? Of course, all the Galois extensions we've looked at so far are just finite, and that's the only ones that we've defined. Let's look at the Galois group. G equals Galois group of K over F. Then the first part, this is not so much part of the actual correspondence, but is a very important part of the theory. Okay, is there's a relationship between the order of the group and the index of K over F. Okay, and the index of K over F is just equal to the order of the group. Okay, so let's just have a look and see how this holds in this example here. Okay, so what is the order of the group here? S3, that is 3 factorial, which is 6. And what is the K over Q? Okay, what's the index of K over Q? Okay, so I guess that's also 6, and if you don't see that straight away, the easiest way, I guess, is to use the fact that you can write a tower. Firstly, if you look at k over this q root of 2, you've just adjoined this, and this has minimal polynomial quadratic, so that's a degree 2 over this, and this is degree 3 over q, so 2 times 3, that gives you your 6. Okay, so this is a lovely relationship between the order of the group and the index of this field extension. And now the other thing is that this correspondence that I set up, that I described here, is actually a bijection in this case. Okay, so that's a wonderful sort of a result. So let me make one more remark here about what goes on. In fact, you can say a little bit more. When you actually try to prove this Galois correspondence, you want to say a little bit more about what goes on here. And that's the following, okay? So suppose now, instead of just looking at G and looking at the order of G, you look at the order of 2 subgroups, which are contained like this, okay? H and H1. So let's look at, for example, H1 is index of H inside H1. Okay, so H is a subgroup for H1, you can look at that. When you prime them, of course, you get intermediate fields. So you get H prime is a field containing H1 prime. And so you can talk about the index of H prime over H1 prime. So remember, this index is just the dimension of this field when you think of it as a vector space over the smaller one. Okay? And actually, this follows fairly readily from parts 2, 1, and A. Okay, so firstly, by part 2, you see. So I guess the key thing here is that if you want just some sort of idea, just to roughly tell you the proof, I won't go through all the details of this, but this will give you enough information for you to piece together the proof. I guess to work out the left-hand side, you just need to know about the order of H1 and the order of H. Okay, and then write them out in terms of things involving the fields, corresponding fields. Okay, so how do you work out the order of H1 and the order of H? So one of the things that you have here is that, well, remember you have a bijection, so that means that you always have L equal to L double prime. So that means that K over L is always a Galois extension. So you can apply part 1 to, instead of K over F, to K over L. K over L, so if you have K and L here, that means for K and L here, that index is the same as the order of the corresponding Galois group of K over L. Okay, so that's basically saying that if you have an H here, if you flip this over to the group side, the subgroup side, if you have H as a subgroup, the corresponding thing here is KH. Okay, H prime is KH, K over KH. Okay, the order of H is equal to the index of K over KH. Okay, fixed by H. So that gives you a handle on the order of the group H in terms of, on the intermediate field side, the index of K over that intermediate field KH. And then using that, you can deduce fairly easily this result here. Okay, so there's quite a lot of abstract theory that's involved here. Let's have a look at an example so you can really see what's going on. And I'll just work with this example that we have here. Okay, so we're going to look at Q, and we're going to adjoin to it the 3 roots of x cubed minus 2. Okay, and then we've got the Galois group as S3, so you can permute these 3 roots as you see fit. All possible permutations exist, and they correspond to a unique Galois automorphism. So we've looked at conjugation here. That's one example where you have an order 2. We'll also need to list some of the other elements, and I guess the easiest way to do that is to look at also the order 3 elements. So let sigma be an order 3 element. We'll make it the one that sends cube root of 2 to cube root of 2 zeta, and that cube root of 2 zeta goes to cube root of 2 zeta inverse, and then this cube root of 2 zeta inverse goes back to cube root of 2. Okay, so let's look at the bijection. Okay, so we'll start on one end. Okay, so the one that I want to have a look at will be the subgroup side, because this is just finite group theory and it's very easy to understand S3. This field, it's an infinite thing and it seems a lot harder to understand. But part of the point of this Galois correspondence is that now, just by studying this finite group, you can say so much about this infinite thing. Okay, so that's rather nice. Okay, so the first thing is that in this side, it's very easy to understand this lattice, this poset of subgroups. Okay, so here you have G, which is generated by this order 3 element sigma and the order 2 element tau. Okay, and what are the subgroups? So there's a unique CeLO 3 subgroup, so a unique group generated by the order 3 element sigma, which is the same as the one generated by sigma squared. Okay, so there's an order 3 element. Okay, and then you have the others are also all cyclic. So remember, if you have any proper subgroup of G, okay, so I guess you can have one, or you can have something that's generated by one of the elements, okay? And then by Lagrange's theorem, you can't get anything else. So the other three elements are all involutions. So it's either tau or sigma squared tau, okay? So that gives you a complete poset of all possible subgroups of G. And now we can say, well, what are all the corresponding intermediate fields? Okay, so that's what we're going to do next. So let's just work out what are all the corresponding intermediate fields. Okay, so the first thing is, so how do we get this side? So we're going this way around, so I've reversed the arrow here. So we just look at the fixed fields. So what's fixed by 1? Everything is fixed by 1. Okay, so that's the biggest thing. So when we do this, remember it reverses inclusion. So here you have containments like this, and now I'm going to have the same sort of lattice, but I've reversed all of them. And so that means that instead of having the smallest thing down the bottom, you have the biggest thing down the bottom here. Okay, that's K. Okay, what's fixed by G? Okay, what's fixed by all these automorphisms? So remember, this is a Galois automorphism. So the only, or Galois field extension, so the only thing that's fixed by all the Galois automorphisms is the bottom field Q. So corresponding to G is Q. And certainly we know that they're intermediate fields, okay? So they're on the outside, okay? They're the extremes, okay? So there's a unique minimum, unique maximum. And then you'll have only 4 things in the middle. So let me just do 2 of them, okay? So I guess one of the things that we saw here was, if you look at this tau, and we primed that, what do we get over the other side? So remember, we computed this tau. That subgroup primed gives you just the intersection with the reals, okay? And that's going to be Q adjoin the real cube root of x cubed minus 2. So that's Q adjoin cube root of 2. And it's a bit of exercise, so we've kind of seen this already here, to see what are, if you use one of the other ones, what you get is you adjoin to Q the other roots of x cubed minus 2. Okay? And in some ways, that's kind of something that you might expect as well. Okay? So, so another thing that you should realize here is that, remember, since L equals L double prime in this case, so you always have K over L as a Galois extension. So this is also Galois, this is Galois over K, but this is also Galois over each of these 3 things. So you can apply part 1 to them, and you can look at what are the indices of this over this. So maybe I'll put the indices in there in blue. So this over this, so this is index 3 here, so this is index 2, 2, 2. And the indices of these as the groups, okay, so that's the order of the group, so that's 2, 2, 2, and they also match up. Okay, this one here is 3, so you need something that's index 3 here for that answer. And if you believe this, well, I guess what you can do is you can say, well, you know there's only one left, so if you can find one, then that's going to be it. That's not the same as those. And of course, the only one that you can see is Q adjoins, so remember zeta is in here, and that's in here. Now the index of this in here is 2. This is a root of a quadratic, and so this has index 3, so this is precisely the one. And you can check actually that if you look at things which are fixed by this, actually zeta will be fixed. Okay. So maybe that's a good sort of a check to see that zeta is fixed by this. So what you know is that zeta of this is this, and zeta of this is this. Okay. So what's sigma of this is this, and sigma of this is this. How do you get sigma of zeta? That's sigma of the quotient of these 2. Okay, so remember zeta inverse equals zeta squared. Sigma of zeta, okay, so you want to say that I want to confirm that this is the fixed field of this, so at least let's check that sigma of zeta is equal to zeta, so that sigma does fix that. Well, zeta is just this divided by this, so sigma of zeta is just, we apply sigma to both of them, so it's just this divided by this. So it's cube root 2 zeta squared divided by cube root 2 zeta, which is just zeta. Okay, and so that gives you the Galois correspondence in this case. And so lo and behold, it turns out that the only intermediate fields that you have between K and Q are precisely the ones that perhaps you would have guessed anyway. Okay, so it's just these, other than K and Q, just these four that you see here. Okay, so you may think, okay, that's really great. It's a pretty neat result, actually. But what does it do for you? Okay, so let me tell you some applications, because this gives you a little bit of an idea about why this is quite an interesting result. Okay, so as I said, this is an infinite sort of an object, and there are lots of elements in here. So let's just pick one. Alpha equals cube root of 2 plus cube root of 2 zeta. Okay, and maybe you want to say, okay, so this element, what's its minimal polynomial? Well, at least what's its degree? Okay, what's the subfield of Q generated by alpha, for example? Well, it's quite easy to say. Well, what is the subfield of Q generated by alpha? So it's got to be one of the fields that you see here, one of the 6 fields that you see here, and it's not Q. Okay, and then you kind of think, well, can it be any of the ones here? And if you look at it, of course, it can't be. Okay, it can't be any of the ones that you see here. So that means it has to be the whole of K. Okay, so it's the whole of this. And once you know that the degree of this of Q is 6. So that means the degree of the minimal polynomial of alpha over Q is also equal to 6. Okay, so that's a rather nice result that you have. And in fact, you think, oh, this is a pretty neat trick, right? What's sort of like the general result that you can get from this? So there is a general theorem that you can actually get from this, and that's called the primitive element theorem. Okay, so this is sometimes proved without Galois theory, and sometimes when you do Galois theory, that's the treatment that's given. I believe that's the treatment in my supervisor Mike Arton's algebra book. But you can also set up Galois theory differently. So there are different ways to set up the proofs, which I'm not going to go through. Okay, so what is the primitive element theorem? If you haven't seen it before, this is a statement. Suppose you have K over F is a finite Galois. Actually, you can do this even when you have a separable extension, a finite separable extension. So suppose let's start with a finite Galois extension. Then there exists a alpha, an element of K, such that K equals F of alpha. In other words, it's a simple extension. So this is actually true for separable. Okay, so well, that's a wonderful result. And the basic idea is kind of what you see here. Okay, what you do is in this example, what can you do? Well, what you do is the following. Okay, to try to find a primitive element, how do you do it in this sort of case here? What you do is you look at all the subfields, intermediate fields, other than this one here, and you want to try to find an element which is not in any of them. So basically, you want to look at the unions of all those subfields, okay? And then you want to say that the union is not all of K, and then you're done, okay? So how do you do that? So let's just look at first in the Galois case. Okay, so if you're in the Galois case, what happens is that the set of intermediate fields is going to correspond to the subgroups of a finite Galois group. So it's a finite set, okay? Now suppose for the moment that this bottom field here is going to be infinite. Okay, so for example in characteristic 0. Then if you take the union of all proper intermediate fields, you're looking at a finite union of proper vector subspaces of this. And you know that if you have a union of a finite number of proper subspaces, you cannot get the whole space here. Okay, that's something that you're seeing. So if it turns out that this is finite, well then you have to do a little bit of a slightly different argument, but it's still true. And that proves the primitive element theorem in the Galois case. So what happens if you're not in the Galois case? Okay, so suppose you're not in the Galois case, for example, this is not Galois. Then what do? Okay, so in this case, well, of course, it's given as a primitive via a primitive element, but maybe we wrote it in such a way that it doesn't look like that, okay? So what you do in general is that you can say, well, okay, so I don't, so that's be like an extension you're looking at. What you can do is you can take the Galois closure. And then in that Galois closure, you can look at all the intermediate fields, and that will contain all the intermediate fields between the original pair that you had. And since that's finite, you can apply the same argument. And there you get a primitive element. So this alpha has got a primitive element. Okay, something which generates the field, a single element that generates the field. So as I said, the proof is fairly technical in most Galois theory courses. It will take several lectures to prove and requires quite a bit of work. And I think there are lots of resources that you can do to find out about the proof, but it's something that you really have to work yourself through, and it's best to read through rather than see presented in a video like this. But I do want to give you some sort of words of advice about how this proof goes about, and enough to sort of give you a sense of why you might expect it to be true and how it might work out. So hopefully the way I've set out these basic facts makes it pretty clear that, well, you're hoping that something like this should be true. This is something that's fairly easy to prove, okay, this basic fact here, which gives you this these maps going in opposite directions. Okay, so firstly, this is something that you have fairly cheaply, maps going in opposite directions that reverses inclusions. And then the fact that at least when you apply it twice, even though you might not get back to where you started, you have this relation that the double primed object is at least as big as the original. Okay, so the next thing that you do is to force equality here, you need to control, in this case, the indices. So either the index between a subgroup pair or a pair of intermediate fields. Okay, if for example you know that the index of this over this is 1, then you're done. Okay, right? That's essentially what you're doing. So you need good control. So basically you want to have results like this. Okay, you want to have a result like this, and more generally this is the type of result that you have. So the proof, usually it will have some technical details associated, but one way to do it is you control the indices very carefully. So let me give you an idea of what's involved in controlling indices. So suppose you've already proved the primitive element theorem, otherwise you have to use a bit of induction and taus or field extensions and things like that, and you have k equals f of alpha. And let's just see how this result gets proved in that case. Okay, so in that case, what happens? Okay, so you're considering a Galois extension of this form, which is simple. So what is the order of the Galois group in this case? Okay, so firstly, all the Galois automorphisms are completely determined by what they do to that generator alpha. Okay, and all it can do is send alpha to another root of the minimal polynomial of alpha. Okay, so it's restricted to sending this alpha to one of the degree of this minimal polynomial things. And being Galois means that you can send it actually to any of them. Okay, so that's one of the things that we have. It's going to be you can send it to any of those things. Okay, so since you can send it to any of those things, okay, you have this equality here. But what is the degree of this minimal polynomial? Okay, it's also equal to, since f alpha equals k, it's just the index of f in k, and that gives you part 1 in this particular case. And so there you have the Galois correspondence, one of the key tools in Galois theory, which allows you to use symmetry to understand a field extension. I hope you enjoyed this adventure in pure mathematics.